As the first example of using Ampere's law, I'm going to look at a familiar situation, and that's a straight, infinitely long wire carrying a current I. And you say, well, I already know that. Yeah. But it might happen that you forget what the magnetic field is like. Uh, so one use of Ampere's law is to just help you remember the result of the infinitely long straight wire. So I'm going to choose a closed curve going around it in the circular path. Just have to remember, because of the high degree of symmetry on this, the magnetic field grabbed the wire, thumb pointing in the direction of the current flow, and then the magnetic field swirls about it, like on the surface of a cylinder, uh, that in this fashion that's given probably best when I look at it from the top view. So looking down, the magnetic field is going in this direction. And I usually, when I have that, I usually choose the direction that I'm going to go around a closed curve. I choose the symmetry point, which is the center of this of the wire, and then I go out perpendicular to it a distance r, and have a closed curve that I walk around in the same direction that the field is. And that usually makes the calculation a little easier. You don't have to do that, but that's what I usually do. And if you do that and you use the convention, this closed curve C encloses an area. And we need areas are vectors, and so we need to define the perpendicular to that area. And again, you use the convention, use the right-hand rule, grab the curve C, that's the dashed line, and in the direction you're going to go around it, with your thumb pointing in the direction you're going to integrate around, and then your fingers of your hand will naturally curl up through the area in the direction perpendicular to the plane of the normal to it. And so I indicated that here. And as I said, I usually try to choose things so that the current flow and normal are in the same direction. Just makes things a little bit easier. And so then I know Ampere's law. Integral of B dot dl around this closed curve is equal to mu naught times the total current cutting through the area S enclosed by that curve C. And by the symmetry, this is around that closed curve. B is the same everywhere, so it's B of R in the theta hat, if you will, and dl is dl in the theta hat, and so one has that. But I'm on a closed curve that's at constant R, and so I've got B of R here, but R is constant all along this curve C, and so a function of a constant is also a constant, and so I can pull that outside. And then mu naught, well, there's only one current cutting it, that's I. It's going in the same direction as n hat, cutting through the surface, and so it's a plus I. And then we get B of R integral dl, all the way around that closed curve. But all the way around the closed curve is just the circumference of a circle of radius r. And so add up all the dl's all around it is just 2 pi r. And we're back to our old familiar Ørsted result for a long infinite wire. Well, sometimes that's, you may or may not consider that easier, but oftentimes I somehow forget this, whether it's a 2 pi or 4 pi, etc. But I do remember Ampere's law, and so I can always reproduce it and find out what the exact expression is for the case of this infinite wire using Ampere's law.